Hello everyone, and welcome back to Calculus BC. This lesson 14, we're going to start talking about integration using U-Sub. I have to say that U-Substitution is one of the most important concepts that you will learn in calculus, whether it's AB or BC. So I'm going to go ahead and get started with our first example. So we're going to start with example number 4, and when we look at this example, we're integrating 5x squared plus 1 quantity squared times 10x dx. And so what we could essentially do here is we could FOIL this out, we could distribute the 10x, and then we could use the power rule, right? We can integrate using the power rule. But let's say that this is not a square, and let's say this is to the 12th power or the 22nd power. You're not going to want to be able to do that. So we're going to actually use substitution here. So one of the things I want to stress with you guys really quickly is you have two functions. You have a 5x squared plus 1, and your second function is 10x. So when you're trying to figure out what u is, what we want to make u, the first question I always ask myself, especially with polynomials, is one of the function's derivative also a function? So is one function the derivative of the other? And the answer is yes, right? The derivative of 5x squared plus 1 is actually 10x. So if the derivative is setting somewhere in the integral, then you want to make u equal to the function that we can actually see the derivative inside the integral. So u is going to be equal to 5x squared plus 1. Another clue, and this doesn't always work, but another really helpful clue that this was our u that we want to do is because we're raising this to a power. So over here, example number 5, we see that 9 minus x squared, that is raised to the 1/2 power, right? That's raised to the 1/2 power. But we'll get to example 5 here in a second. So let's continue with number 4. So once you've done u, and you will always, in all derivative or integrations that you guys do in the class, if you write u, you're going to always write du. So the derivative of this is going to be 10x, and then it's going to end up being dx. And the reason why, and let me just say this for one time, and then this is the first and last time I'm going to say this, I want to implicitly differentiate this. So I want to implicitly differentiate this. So I'm going to get du over dx, right, as like we did with implicit differentiation. Then I'll take the derivative of this, which is going to be 10x plus 1, so the derivative of plus 1 is going to be 0, and then we're going to do dx over dx. And so dx over dx actually just ends up becoming 1, right? So I can actually get rid of that. And then all I did, ladies and gentlemen, to get what you see right here is that I go ahead and cross multiply, and now the dx is on the other side. So I'm going to automatically, from every problem here on out, I'm going to write my u down, and then I'm going to write du immediately, and then I'm going to find my derivative of my function, and I'm going to always write a dx. And this is the reason why. This is the reason why, because we're just cross-multiplying. We're implicitly differentiating this, and we're cross-multiplying the dx. So I just want to say that really quickly. So when you guys do u and you do du, you always want to just write out the derivative and then always write dx. And just get in the habit of doing that, because that's always going to work for us. All right, so this is called U-Substitution. So we really don't know how to integrate this, but we can use U-Substitution here. So we've already designated 5x squared plus 1 as our u. So I'm going to go ahead and write a u here for this. And a square is still a square, so we're going to go ahead and do a square. And why I like this question, ladies and gentlemen, is that right now, this 10x dx that we see right here is actually equal, and here it is right here, 10x dx is actually simply equal to du. So this is simply going to be du. So this integral can be rewritten as the integration of u squared du, which is absolutely awesome because this is something that we can easily integrate. So I'm going to go ahead and integrate this. And so I'm going to get u cubed over 3. And with our plus c, we're at the plus c. And then I'm going to go ahead and just rewrite this one more time as 1/3. And then it's going to be u cubed plus c. So our answer to our problem, ladies and gentlemen, is that once we've done this, we're going to now write the 1/3. But our question was given to us in terms of x, so we need to replace this u with the function 5x squared plus 1. And then again, we have our cube here plus c. So the answer to our problem is what you see right here. And if you were to take this derivative, you're actually going to get this back. We move the 3 down, the 1/3 and the 3 cancel. So we're left with 5x squared plus 1 to the 1 less power, hence the 2. And then by the chain rule, you're going to multiply by the derivative inside, which is the 10x. So that's what you do for this question. Okay, so it's actually pretty awesome problem to do. So now let's look at this question right here, and we'll go through it pretty quickly because we're going to reference this. So we have two functions. Now, the derivative of 9 minus x squared is actually negative 2x. If we are just simply missing a constant, that's totally fine. So as long as our function is still there, we're good to go. So let's go ahead and make u equal to 9 minus x squared. And just like in the previous example, I'm going to do du is equal to, well, the derivative of 9 is just 0. Derivative of negative x squared is going to be negative 2x. And just like before, ladies and gentlemen, I'm going to go ahead and always write the dx out because that's going to be matched to what we have right here. So we have the x and the dx. We have that. So all we have to do to see what u is, because remember, we're eventually going to substitute for du, is let's go ahead and divide by negative 2. And so we're going to get negative 1 over 2, or negative 1/2 du is equal to x dx. And now, ladies and gentlemen, we're actually ready to start subbing in like we've done in the previous example. So I'm going to go ahead and do our square root, or not square root, integration. And now we're going to do our square root. And remember, this right here is simply u, so we can rewrite this as u. Now, what is x dx? Well, x dx is equal to negative 1/2. Sorry, let's write that better for us. Negative 1/2 du, right? So we're just substituting. It's right here on the right side, so we're going to go ahead and write this down. So we got the integration of the square root of u times negative 1/2 du. One of the actual properties we can use with integrals is that we can always pull out a constant. We can always pull out a constant. Never variables, but we can pull out a constant. And so anytime that I do this in my future examples, I'm just going to go ahead and pull out this number. Okay, pull out this number. And so I'm left with u to the square root of u, which is just u to the 1/2 power du. And now, ladies and gentlemen, we're back to a problem like this. It's super easy to integrate this, right? So we're going to go ahead and do negative 1/2. And I'm going to integrate this as u to the 3/2. And I'm going to go ahead and put a 2/3 on the outside. Remember, it's really divide by 3/2, right? Whenever you integrate by one extra power, you divide by that same value. Well, if you divide by 3/2, you're multiplying by 2/3. And then we do a plus c. And I'm going to go ahead and pull up the 2/3. Right? Why not do that? So we're going to have negative 1 over 3, right? So the 2's cancel out. And then I'm left with u to the 3/2. Now, students ask, should we distribute the negative 1/2 to the c? And you absolutely could, 100%. But that's just going to give us another c value. So I'm just going to leave it at c, but yes, you could absolutely write a negative 1/2 c as well. And you will take into account when we start doing differential equations, when we have a value here, then we would incorporate that absolutely, which you guys will see later in the course. And so finally, ladies and gentlemen, all I have left to do now is go back and substitute back in. So I've got my negative 1/3. I know that u is going to be equal to 9 minus x squared. So I'm going to go ahead and replace u with 9 minus x squared to the 3/2 power, and then plus c. Because again, if you take the derivative of what I've written in purple right here, it doesn't matter what the c value is. So if it's negative 1/2 c, it's still a constant. It's going to go away anyways because we're just left with this right here because this is still a definite integral. Okay, so that's an example of that. All right, so we're going to do one more example, and then we're going to end the video. So there are many awesome examples that I could do for these videos, but I want to do something like question number 5 because we haven't talked about one where it's just really one function, right? So it's got 1 plus 2x squared, 1 over that dx. And so, ladies and gentlemen, if we don't have two functions, but the function that we do have, if that derivative is simply a constant, which it is what it is, then that's what we're going to use for our u. So we're going to go ahead and do u is equal to 1 plus 2x. And as I said earlier in the video, this function is actually raised to a power, so we can absolutely think about that as also going to be our u for the problem. And sometimes u sub is not the right way of doing the problem, and as we move through the course, we're going to get into some strategies on that as well. So right now, like I said, this video, all the questions that we're doing is a u sub problem. So we get 1 plus 2x, and so I'm going to go ahead and take the derivative of this, and I'm going to give you 2 dx. And so just like in the previous problem, ladies and gentlemen, I'm going to go ahead and take out a 2. I'm going to divide by 2 because I don't have a 2 here. Now, if there had been a 2 right here, then you would have left it alone. But in our integral, when we substitute in, we don't have this necessarily 2, so we have to get rid of it. And so we're left with this. And so when you guys are integrating, when you're integrating stuff, you should be able to figure this out pretty easily. make sure that everything's taken care of. So we still got our integration, we got our 1 over, and now this is our u. So we're going to do u squared. And the constant, I always just go ahead, as I said in the previous example, I go ahead and just pull the constant out. So we have a 1/2 here. Because dx is actually equal to 1/2 du. So I could have written 1/2 du in here. I'm going to go ahead and write u, but then I would immediately pull out the 1/2. So I'm telling you guys right now, to save yourself some time and energy, you can always pull a constant out when you do the problem. And then to finish this question up, we're going to go ahead and rewrite this as u to the -2 du. And we have to be very careful, again, ladies and gentlemen, when we do this particular problem, that when we do this, we're adding 1 to the power. And we also remember that we have to integrate, right? We're adding 1 to the power, so it's going to be -2 plus 1 is going to be -1 over -1 plus c. And so I can pull out this -1, right? So I can pull out a -1, and I'm left with 1 over u plus c. 1 over u plus c. And so all I have left to do now is plug in what I have, right? For our u, we can substitute in our function, and so we're left with -1/2, and then we have 1 over 1 plus 2x, parentheses, plus c. And so just to write that a little bit nicer for us, so we're all in one fraction, we can write it like so, plus c. Okay, so there is the answer to that problem. So hopefully that makes sense to you guys as well. So what happens if we have a function, that doesn't work out nicely like this? So let me give you guys one more example. Actually, I fibbed. We're going to do one more example where we don't have our derivative and the derivative is not a constant. So let me show you guys one more example. So I know I'm moving around quite a bit in this note set here, but now we're looking at example number 3 where we have the integration of x times the square root of x plus 1. One of the things you absolutely cannot do, and as a calculus student, I know you guys know this, you cannot distribute the x inside of here, right? This is, when I taught Algebra 1, I was thinking, if you're under the square root, you're grounded, so you can't play with the students that are not grounded. So they cannot interact with each other, right? This one is not grounded, and these students are, or this term is. We still have two functions. We have x, and we have the square root of x. Well, the derivative of x is 1, so that doesn't help us, and the derivative of x plus 1 is also 1. So one of the functions is not a derivative of the other one. Now, you may think about trying another method, but if we make u equal to x plus 1, now remember, again, why did I choose x plus 1? It's because it's what's underneath the radical. It's what's raised to a power. And just like before, we're going to do du is going to be equal to dx. So again, I implicitly differentiate this, but I get du equals to 1 dx, right? And I went ahead and cross multiply to get the dx here. So if I wanted to start substituting over here, right, if I just want to go ahead and do this, so I can go ahead and say I've got the square root of u, which is this, and awesome, dx and du are actually equal to each other. So what we have to do is we still have this pesky little x that we have to deal with. Well, I know, and you guys see here, that we have a relationship. We know, because remember, the whole thing, again, is called U-Substitution. So we want to be able to rewrite everything and substitute everything in terms of u. So I have what I call my bridge step. This bridges it's my relationship between my u and my x. I know that if I just simply solve for x, I get that x is equal to u minus 1. So I can absolutely rewrite x as u minus 1. So this is always another option, that if you do have an x or an x squared or something here, and you have a relationship where you can easily solve for it. Now, will this help our initial problem? This one does, but sometimes you may end up with a bigger mess than you started with, and then U-Substitution is not the best way of doing the problem. There could be something else involved, like integration by parts or partial decomposition, but in this case it is. So if you look at this, is this easy to solve? You got to always ask yourself, is this easy to integrate? And the answer is yes. So I'm going to go ahead and rewrite the square root of u in front, just so we can see every single step. So a times b is the same thing as b times a. And I'm going to say it one more time, that u is now to the 1/2, and then u minus 1 du. Okay, so again, and we always check here and say, do we have everything listed here? Yes, u, x plus 1, du is equal to dx, and then x is equal to u minus 1. And so all we do now, ladies and gentlemen, is actually just use our properties of our exponents, and we get u to the 3/2 minus u to the 1/2 du. And please don't forget to integrate. We still have to integrate this. So just like before, we're going to go ahead and not write that. We're not going to write that. We're going to integrate this, so it's going to be u to the 1 more power, right? 3 halves plus 2 over 2 is 5 halves. And instead of dividing by 5 halves, I'm just going to go ahead and multiply by 2 fifths. That's the easiest way to write that fraction out. Minus u to the 3 halves power. Again, I'm integrating. So again, dividing by 3 halves is the same thing as multiplying by 2 fifths. Oh, sorry, 2/3 plus c. Plus c. So our final answer for this problem is going to be 2 fifths. And then we're going to replace u with x plus 1 to the 5 halves power minus 2/3. Again, we're going to replace this u also with x plus 1 to the 3 halves power plus c. So there is our u sub little guide for indefinite integrals. So hopefully that's helpful. And in the next video, we're going to talk about u sub for definite integrals. So I'll see you guys in the next video.